Hello there. Today, we are looking at the mind map of the chapter, Equilibrium. It is the 7th chapter of the chemistry syllabus for students of grade 11 Cbse. Let's roll. So, this is the mind map that we are going to be working on. It is a huge mind map and has a lot of information. Therefore, we'll divide this into 11 sections. First, I'll explain the tree and then all the boxes that are joined to it. So, in the chapter Equilibrium, we will first look at the definition for equilibrium and equilibrium in chemical processes. After that, we'll move on to the types of equilibrium, which are homogeneous, heterogeneous, physical, and chemical. Then, we will move on to the equilibrium law or law of chemical equilibrium. This is very important. Keep that in your mind. After that, we will move on to the equilibrium constant. After that, we will hit the topics predicting the extent of a reaction and predicting the direction of a reaction. Then we will move forward to the practical based part, calculating equilibrium concentrations. And then we will move on to the relationship between equilibrium constant K, reaction quotient Q, and Gibbs energy G. After that, we will move on to the facts affecting equilibria. Then, we will move on to the final phase of this chapter, acids and bases. After that, we will look at a short footnote regarding the pH scale. So, that was the tree of this chapter, and now we'll move on to the first box. Under given set of conditions and equilibrium in chemical processes. Equilibrium under a given set of conditions states that if a chemical reaction is carried out in a closed container, a constancy in some observable properties such as color, pressure, etc. is observed. Such a state is referred to as equilibrium state. Suppose we have a container which is closed on all ends, and we do some reaction here, a reversible reaction. So after some time, you'll notice that properties such as color, concentration, pressure, temperature, etc. will be the same, even though the reaction is running. This state is known as equilibrium. Now, let's move on to the next topic, equilibrium in chemical processes. Now, the thing that you should note in this is that the equilibrium in chemical processes is dynamic. What it means is that chemical reactions reach a state of dynamic equilibrium in which the rate of forward and reverse reactions are equal and there is no net change in composition. So, back to this reaction. Suppose I have a reaction. CaCO3 or calcium carbonate gives you CaO, calcium oxide, plus CO2, carbon dioxide. When we reach the state of equilibrium for this reaction, the reaction does not stop. Rather, the rate of the forward reaction, the decomposition of calcium carbonate into carbon dioxide and calcium oxide, will be the same as the formation of calcium carbonate from the products. So this form of equilibrium is known as dynamic equilibrium. So once you've understood equilibrium in chemical processes, we'll move on to the types of equilibrium. In types, we will look at physical equilibrium, chemical equilibrium, homogeneous equilibria, and heterogeneous equilibria. Let's expand this. Now, with regards to physical equilibrium. Equilibrium set up in physical processes like evaporation of water, etc., are known as physical equilibria. Now, these do not have a chemical reaction. These are everyday physical activities that we can see, such as melting of water or boiling of water. Now, in physical equilibria, we will look at three types of changes: solid to liquid and back again, liquid to gas and back again, solid to gas and back again. Now, for solid and liquid stages, we can use water. And from solid to gas, that is sublimation, we can use naphthalene, iodine, ammonium chloride, etc. Now, the things that you need to know about physical equilibria are: physical equilibrium is possible only in a closed system at a given temperature. Suppose you're boiling water and you want the equilibrium to be maintained. You can't just do that by opening the container up and letting the water vapor go out. That would ruin the equilibrium. You need to close the container so that the equilibrium is maintained. The second thing is that both the reactions occur at the same rate. Physical equilibrium is usually dynamic, so that the forward reaction and the backward reaction both occur at the same time at the same rate, so as to give a net reaction of 0. All measurable properties remain constant. Measurable properties are properties that we can measure, such as volume, pressure, temperature, concentration, etc. When equilibrium is attained, one of its parameters remain constant at given temperature. So for instance, we have a reaction. Now some parameter of the reaction, such as temperature or pressure, would remain constant at a given temperature to maintain the equilibrium of the system. The last point here says that the magnitude of such quantities at any stage indicates the extent to which process has proceeded before reaching equilibrium. Now this point will be taken up in the 6th portion of the mind map, where we look at predicting the extent of a reaction. Now, from physical equilibrium, we move on to chemical equilibrium. Now, in chemical equilibrium, the main thing that you need to understand is that the speed of the forward reaction would be equal to the speed of the backward reaction. When this condition is satisfied, you get chemical equilibrium, which is dynamic. Now, the characteristics of chemical equilibrium are: chemical equilibrium can be achieved from either side. You can either keep some reactants and form a product, or you can keep a product and start to split it to its reactants. Both ways you can achieve equilibrium in the right set of conditions. And the second point is, as we stated, the chemical equilibrium is dynamic. The third point states that there is no change in concentration of various species. As we have conserved volume, pressure, temperature, etc., the concentration of the equilibrium remains the same. The next point states that observable physical properties become constant. So this is with regard to properties such as pressure, temperature, volume, etc. These are physical properties. So when we have a chemical reaction in chemical equilibrium, these properties would remain constant. Equilibrium is attained rapidly by the presence of catalyst. So suppose you have a certain reaction going on and you want to speed up the process of reaching chemical equilibrium. What you can do is add a catalyst. A catalyst is any substance that does not participate in a reaction but can change the rate of the reaction. So that completes chemical equilibrium. Now, we will look at the differences between homogeneous equilibria and heterogeneous equilibria. In homogeneous equilibria, reactants and products are in the same phase, while in heterogeneous equilibria, reactants and products are present in 2 or more phases. An example for homogeneous equilibria can be H2 plus I2 gives 2HI. Now, in this scenario, all of these are in the same state of matter, that is, they're gases. While in heterogeneous equilibria, reactions such as CaCO3 decomposing to give carbon dioxide and calcium oxide would have different states. CaCO3 is solid while CO2 is gaseous would prove that this is heterogeneous, while the earlier reaction that we wrote here proves that this reaction is homogeneous. So that's all about the types of chemical, physical, homogeneous and heterogeneous equilibria and their properties. Now, we will move on to the equilibrium law or the law of chemical equilibrium. This is the fourth part. Let's expand it. The law is stated as such. At a given temperature, the product of concentrations of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of concentration of the reactants raised to their individual stoichiometric coefficients has a constant value. Now this is a mouthful. So therefore, to represent it in a formulaic form, they have given Kc is equal to C raised to C plus D raised to D divided by A raised to A plus B raised to B. For the reaction, AA plus BB gives CC plus DD. Now, in this formula, the letters in uppercase A, B, C, D represent the elements participating in the reaction, and the lowercase letters A, B, C, D refer to the coefficients, the stoichiometric coefficients of the reaction in balanced state. So these coefficients become the exponents in this formula, and the bracket here represents the concentration of the element. So the concentration of C raised to its coefficient plus the concentration of D raised to its coefficient. C and D are products, by the way, so they are written in the numerator, divided by concentration of A raised to its coefficient plus concentration of B raised to its coefficient. These are the reactants. Now, the left-hand side is given as Kc. Kc is representative of equilibrium constant. Now, to learn more about equilibrium constant, we will move to the fifth part of this mind map. So, back to this law. The law states that when you have a chemical reaction containing reactants and products, to find its equilibrium constant, you multiply the concentration of the elements of the products raised to their stoichiometric coefficients. If they have a number beside them, you will add that number as the exponent. And we divide this by the sum of the concentration of the reactants, the ones on the left-hand side of the reaction. Make sense? Good. Let's move on to equilibrium constant. The constant value in the reaction is known as equilibrium constant. So, in the previous law, we have got that the LHS of the equation is Kc. The same Kc is equilibrium constant. Now, a unique thing to note is that equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for reaction in the forward direction. So, since our reactions here are mostly both forward and backward reactions, as they are reversible, equilibrium constant for a backward reaction would have the same value as the equilibrium constant for the forward reaction. The only difference is the backward reaction's equilibrium constant is inversed. Now, the applications of equilibrium constant is stated below. Equilibrium constant is applicable only when concentrations of the reactants and products have attained constant value at equilibrium state. So after we undergo a reaction and the reaction achieves its equilibrium state, the concentration then would be applicable to be calculated to get the equilibrium constant. So the reaction has to reach its equilibrium state before we can identify its equilibrium constant. The second point states that the value of Kc, equilibrium constant, is independent of initial concentrations of the reactants and products. So it doesn't matter how many reactants or products you have added before you start the reaction. They have no consequence whatsoever on the equilibrium constant. It is not dependent on that. The equilibrium constant is temperature dependent. So if you increase the temperature, the value of the equilibrium constant may vary. Now, for the first condition, that for the reverse reaction, the equilibrium constant is the inverse of the equilibrium constant for reaction in the forward direction, we write Kc reverse as 1 by Kc. So this is known as the inverse of the equilibrium constant. The final point here says that equilibrium constant for a reaction is related to equilibrium constant of its corresponding reaction. So the value would still be the same. It would still have some relation. The equilibrium constant of both the reactions, the forward and the backward, would have a relation. That is what the last point says. Now, from equilibrium constant, we move on to the next stage, predicting the extent of a reaction and predicting the direction of a reaction. To predict the extent at which the reaction moves, as in how much of the reaction is complete or not complete, we use the following three conditions. If the equilibrium constant is less than the order 10 raised to minus 3, 1 by 1000, the reaction is considered to have not proceeded at all or have proceeded rarely. So that means the quantity of the reactants would be more than the quantity of the products when we reach equilibrium. But if Kc, the equilibrium constant, is greater than 10 raised to 3, it's greater than the order of 1000, the reaction proceeds nearly to completion. So in this scenario, there will be a lot more products than the reactants. The products nearly dominate the equilibrium state, so much so that in some cases, the reactants are not even found out. Now, if Kc is between the order 10 raised to minus 3 to 10 raised to 3, the reaction is at equilibrium. Now, this means that the quantity of the reactants and the products are comparable. Sometimes the reactant may be more than the product, but only by a slight amount, and vice versa. So this tells us how far the reaction has progressed. But what if you want to know in which direction the reaction is moving, whether it's forward or backward? For this, we use another value called reaction quotient. Reaction quotient here is represented by the term Qc. Qc has the formula C raised to C plus D raised to D divided by A raised to A plus B raised to B. However, the reaction quotient will only have that value. The equilibrium constant, Kc, can be altered by the values R and T, ideal gas constant and temperature respectively, in the gaseous state. So, if the reaction quotient is less than the equilibrium constant, the net reaction goes from left to right. It goes forward. But if the reaction quotient is greater than the equilibrium constant, then the net reaction goes from right to left, backwards. If Qc, the reaction quotient, is equal to equilibrium constant, then there is no net reaction. It goes both forwards and backwards at the same rate, and we reach equilibrium. So that concludes this part. So from predicting the extent of a reaction and the direction of a reaction, we will move on to the steps of calculating equilibrium concentrations. The first step for calculating equilibrium concentrations is to write the balanced equation for the reaction. The second step is to make a table that lists for each substance involved in the reaction values such as initial concentration, change in concentration, and equilibrium concentration. So once you have written the balanced reaction, we write the initial concentration, the equilibrium concentration, and the change in concentration between the initial and equilibrium concentration. So those values are written below the reaction for each element. Step 3 is to substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve. So we'll make an equilibrium reaction and we'll add the equilibrium concentrations. We will place there one by one and we'll start solving to get the equilibrium concentration for the whole reaction. The fourth step is to calculate equilibrium concentrations from the calculated value of concentration of substances. This involves the calculation step. The final step is to check whether your answers are correct. Check your results by substituting them into the equilibrium equation. So in steps 2, 3, and 4, we may deal with variables such as x and y. After step 4, you will get the values of x and y. In step 5, you need to substitute them into the initial reaction, the initial balanced reaction, and then find out whether it matches. If it matches, then your answer is correct. Now, we have a couple of other topics here, such as buffer solutions and solubility product. Let's move to them. A buffer solution is a solution which resists. I'm sorry, it's written reside, but it's actually resist. Buffer solutions are the solutions which resist change in pH on dilution or addition of acid or alkali. So suppose you have a buffer solution and you add a small amount of acid or a small amount of base, or you try to dilute it with water, it resists the change in pH. No matter if you add those, the pH will not change. It resists change in pH. It will try to conserve its pH. An example for a buffer solution is human blood. That's right. If the human blood is a buffer solution against resistances in pH inside our body, it keeps our body's pH perfect. Solubility product, or KSP. If we have a sparingly soluble salt, such as silver chloride, AgCl, which does not usually dissolve in water that easily, the solubility product is the product of molar concentration of ions raised to the power equal to number of times of each ion. So suppose in AgCl, we have 1 mole of AgCl. So we write the solubility product as the concentration of Ag and Cl raised to their respective ion concentration, such as moles, etc. So if you have 1 AgCl, you write concentration of Ag 1, concentration of Cl 1. So that is what we mean by solubility product. So from calculating equilibrium concentrations, we move on to another important topic, the relationship between equilibrium constant K, reaction quotient Q, and Gibbs energy G. Now, if Gibbs energy G is negative, the reaction is spontaneous and proceeds in forward reaction. So if you have a reaction here and it has its Gibbs energy value as negative, then you don't need to start the reaction. It will start by itself and it proceeds forward. But if the value of Gibbs energy is positive, you have to start the reaction as it's non-spontaneous and it moves in the backward direction. You need to provide some heat for the reaction to occur, and even then it moves backwards. Now, if the Gibbs energy is 0, we say that this reaction has achieved equilibrium. Now, this formula here, the equilibrium constant K is equal to E raised to minus delta G naught divided by RT, gives the equilibrium constant in terms of reaction quotient and Gibbs energy. E is a constant number, which is equal to 2.303 something. It is an endless number. And delta G naught refers to the change in original Gibbs energy. R refers to the ideal gas constant, and T refers to the temperature. So in order to find the equilibrium constant when you have Gibbs energy and reaction quotient, what you do is write K as E, the number E, raised to minus delta G naught divided by RT. This whole value is the exponent, and this whole reaction, this formula, gives you the value for equilibrium constant without having to go through the concentration steps. Now, the next thing here is Arrhenius' concept of acids and bases. Now, these topics here are relatively simple and they're easy to understand. Arrhenius is the name of a scientist, and he says that acids are substances which, when you dissolve them in water, they give you hydrogen ions. So if you dissolve hydrogen chloride in water, you get hydrochloric acid, which has H+ ions. And bases are substances that produce hydroxyl ions. Hydroxyl is OH-. Suppose you have sodium hydroxide and you dissolve it in water, you get hydroxyl ions. So that is the basic concept of Arrhenius. He devised this test for distinguishing acids and bases. However, there are other theories which are complementary to these. One of them is the Bronsted-Lowry theory. Now, Bronsted-Lowry says that acid is a substance that is capable of donating hydrogen ion. This is true since an acid has a lot of H+ ions. And bases are substances capable of accepting a hydrogen ion. H+ plus OH- gives you H2O. So they can accept H+ ions. Now, the last point here says that weak acids have very strong conjugate bases. Now, if an acid, such as acetic acid, is weak, it will have a very strong conjugate base to form to neutralize itself. Now, from the relationship between equilibrium constant, reaction quotient, and Gibbs energy, we move towards the 9th part of this mind map, the factors affecting equilibria. Now, these are the factors affecting equilibria of a reaction. The first principle here, Le Chatelier's principle, is extremely important. It states that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to counteract the effect of the change. So if we have a reaction that's in equilibrium and we try to change stuff like temperature or pressure or concentration, Le Chatelier's principle says that the system in equilibrium will try to resist the change by altering the rate of the reaction. So sometimes if it favors the products, then the reaction goes backward. And if it favors the reactants, the reaction goes forward. So that is the basic principle behind this statement. Now, the effect of concentration change. If concentration of reactants is increased, equilibrium will shift in forward direction and vice versa. So if we have some reactants here and we have to convert them to a product, and once the reaction is done, we have it at equilibrium. And suppose we increase the concentration of the reactants, we add more reactants. So what would the equilibrium system do? It pulls the reaction forward. By pulling the reaction forward, it gets more products. That will stabilize the value and keep it at equilibrium. The effect of pressure change is next. There is no effect of pressure change if moles of reactants and products are the same. Suppose you put some pressure, but you still do not change the number of moles of reactants and products, then there is no effect of you putting that pressure. However, if there is a change in number of moles, equilibrium will shift in the direction having smaller number of moles when the pressure is increased and vice versa. So we have a system in equilibrium, and suppose the pressure you applied decreases the number of moles of reactants, then what would the system do? The system would pull the reaction backwards to stabilize the state of equilibrium. The next point is the effect of inert gas addition. If the volume of a system in equilibrium is constant, that is, addition does not affect change partial pressure or molar concentration, equilibrium is not affected. Now this statement says that if you have a system in equilibrium, you add some inert gas, but still the volume is constant, then you have not affected the equilibrium at all. The effect of temperature change concludes this topic. For exothermic, low temperature favors formation of reactants. For endothermic, high temperature favors formation of products. So suppose you have an exothermic reaction and you decrease the temperature. What will it do? The reaction will be pulled from the product side to the reactant side. So it can be forward or backward, which depends on the reaction being a combination or a decomposition reaction. But if it's an endothermic reaction, then the increase in temperature favors the formation of products. So the reactants will form the products if the temperature is increased in an endothermic reaction. Now the vice versa also happens in this situation. And that concludes factors affecting equilibria. Now we will move on to the topic acids and bases. Now in this section we will revise what are acids and bases in general. Acids turn blue litmus into red and liberate dihydrogen on reacting with some metals. You must have seen that. If HCl reacts with a metal, it releases hydrogen gas. And if you put HCl on blue litmus paper, it turns into red. Now what about bases? Bases turn red litmus into blue, taste bitter and feel soapy. Those things that you find in your shower, the soap, those are bicarbonates that are basic. Salts are formed when acids and bases are mixed in right proportion. Lewis acid accepts an electron pair. Lewis base donates an electron pair. So a person named Lewis, a famous scientist in fact, says that an acid accepts an electron pair and a base donates an electron pair. Now some substances are named Lewis acid because they accept electron pairs. After him, Lewis base does the opposite. It donates electron pairs. Now, in an acidic solution, the H plus concentration would be more than the OH minus concentration. In a neutral solution, the H plus concentration will be equal to the OH minus concentration. In a basic medium, the H plus concentration will be less than the OH minus concentration. In these, you see the formula H3O written. H3O is hydronium. So what essentially it is it is the addition of hydrogen plus and water to form H3O plus. So if you see H plus or H3O plus, remember that they mean the same thing with regards to acidic, neutral, and basic solutions. Now, we've completed the stuff that was attached to the tree. However, we have a footnote right here with regards to pH. pH, or hydrogen potential, is essentially the amount, the concentration of H plus ions in a solution. Now in here, it says that the pH of a solution is the negative logarithm to base 10 of the activity of hydrogen ion. Now let me write that out for you. pH is negative log square bracket H plus. So if you know the concentration of H plus ions in a solution, you just need to do a logarithmic function and put a minus value to it to get the pH of the solution. Now, this diagram shows hydrogen reacting with halogens. The size of these decreases. HR is very less than HCl, is very less than HB, is very less than HI. Now R and B stands for other elements. It may be other halogens, it may be some other elements as well. Size increases means that acidic strength increases. So if you have HF and HCl, the size of HCl is more than that of HF. So since HCl has more weight than HF, the acidic strength of HCl is more than HF. And that completes this chapter. It is a very huge chapter, and we hope this video helped you to simplify it for your boards and to some extent your NEET and JEE exams. Did it help you? What more do you want to see? Please tell us your views in the comment section below. Do like the video if it was great. That helps us a lot. Please subscribe to our channel, Brain Blitz Audios, for getting more useful content such as stories, poems, mind maps, etc. Until next time, have a nice day.